Section 10, Defensive Programming. I'm gonna open with a new tab as usual, and here I'm gonna create a new Jupyter notebook. Name is as is that 9, which is 10 already. Defensive Programming. So I got the first one as usual is overview. Second, I'm gonna got here, which is assertions. Next, I'm gonna got which is test driven development, and next I'm gonna got which is pre and post conditions. Here I'm gonna got testing, assertions now, and key points. So from the beginning here, I'm gonna copy the key points to get it from the beginning as usual. Copy that and put in here as a markdown and enter. So I got program defensively. In other words, assume that arrows are going to arrays and write code to detect them when they do. Put assertions in programs to check their state as they run, and add to help readers understanding how those programs are supposed to work. Use preconditions to check that the inputs to a program are safe to use. Use post conditions to check that the output from a function is safe to use. Write tests before writing code in order to help determine exactly what that code is supposed to do. So we got to the beginning, we got an overview. So this time is going to be about 30 minutes and the exercise about 10 minutes. Questions: how can I make a program more reliable? Objectives: explain what an assertion is. Add assertion that check the program state is correct. Correctly add precondition and post-condition assertion to functions. Explain what test-driven development is and use it when creating new functions. Explain why variables should be initialized using actual data values rather than arbitrary constraint constants. So our previous lessons have introduced to the basic tools of programming: variables and lists, file I/O, loops, conditionals, and functions. So what they haven't done is show us how to tell whether a program is getting the right answer and how to tell if it is still getting the right answer as we make changes to it. To achieve that, we need to write a program that check their own operation. Write and run tests for widely used functions. Make sure that we know what correct actually means. The good news is doing these things will speed up our programming, not slow it down, as in a real carpentry, the kind done with lumber, in time saved by measuring carefully before cutting a piece of wood in much greater than the time that measuring takes. So firstly, assertion. The first step toward getting the right answers from our programs is to assume that mistakes will definitely happen and to guard against them. This is called defensive programming, and the most common way to do it is to add assertions to our code so that it checks itself as it runs. An assertion is simply a statement that something must be true at a certain point in a program. When Python sees one, it evaluates the assertion's condition. If it's true, Python does nothing, but if it's false, Python holds the program immediately and prints the error message if one is provided. For example, this piece of code holds as soon as the loop encounters a value that isn't positive. So let's see how it works here. So we run that. You got an error, which is assertion error. So the code is number, which is a list. The total initially is 0. So for number in the list, number, we assert num more than 0, data should only contain positive value. So we put something in there and we make a condition that data should only contain positive values. And when the program encounters something not as we designed for, it's going to raise an error called assertion error. And we know that data should not contain positive, should only contain positive values. That's interesting. Programs like Firefox browser are full of assertions. 10 to 20 of the code they contain are there to check that the other 80 to 90 are working correctly. Broadly speaking, assertions fall into 3 categories. One is precondition. It's something that must be true at the start of a function in order for it to work correctly. A postcondition is something that the function guarantees is true when it finishes. An invariant is something that is always true at a particular point inside a piece of code. For example, suppose we are presenting rectangles using a tuple of 4 coordinates. So we got x0, y0, x1, y1, representing the lower left and the upper right corners of the rectangle. In order to do same calculation, we need to normalize the rectangle so that the lower left corner is at the origin and the longest side is 1 unit long. This function does that but checks that its input is correctly formatted and that its result makes sense. So we got a long function here. Let's define that function inside here. So we just run that function and it's working. And let's see the function look nice. So it's called normalize rectangle and we put in a rectangle. So this function is going to normalize a rectangle that it is at the origin and 1 unit long. Input should be the format like that, and define the lower left and the upper right corners of the rectangle respectively. So we got assert the length should be 4. Rectangle must contain 4 coordinates. So if we don't input 4 parameter, we will get this assertion error. Then x0, y0, x1, y1 is equal to rectangle, and we design another assert which is x0 is smaller than x1, and we got invalid x coordinates. So if x0 is smaller than x1, we're gonna got an invalid x coordinate. Similar, y0 is smaller than y1, we're gonna got an invalid y coordinates. Why? Because, and then we get the axis, the difference between x0 and x1. By the way, this is very good example in mapping as well. The x is y1 minus y0, and then if the x is larger than the y, what we're gonna do is we're gonna scale the float of the x over the y, and then the upper x and the upper y is gonna be 1 and scale. So the upper x is gonna be 1 and the upper y is gonna be dx over dy. Else the scale is gonna be that one and the upper x and upper y is gonna scale and that one. So it depends on if the dx is larger than the y, but if dx is smaller than the y, we're gonna use that one. So basically it's gonna scale the normalize the rectangle. Then we got some more assertion error, which is if upper x is smaller than 1 and larger than 0, calculation upper x coordinate is invalid. So this is the true condition. We want something like this. If it's not like this, it will throw an error. Okay, so we want something like this, and if it's not like this, we will not throw an error. Similar, we want upper y is smaller than 1 and larger than 0, and if it's not happening like this, it's going to throw an error. Similar, we will return, and finally we'll return 0, 0 and upper x and upper y. So the preconditions on line 6, line 8, and line 9 catch input variables for invalid inputs. So now we can run it in Python. We got an error which is rectangle must contain 4 coordinates. That's so interesting. And again we run that, and we got invalid x coordinate. Why? Because this is x1 and x2, x0, x1. So this one should be larger than. Okay. So the post conditions on line 20 and line 21 helps us cut bugs by telling us when our calculation might have been incorrect. For example, if we normalize a rectangle that is taller than it is wide, everything seems okay. So we do that and we call that function. So we got that one, seems everything is okay. But if we normalize one that wider than it is tall, the assertion is triggered. So we got that. It's gonna be triggered assertion because this one is smaller than this one, and the calculated upper y coordinate is invalid based on code. Rereading our function, we realize that in line 14 should divide dy by dx rather than dx by dy. So we're gonna copy that. We wanna define the function again, and that one is to be dy dx. In Jupyter Notebook, you can display line numbers by typing Ctrl M followed by L. So you put Ctrl M, L, sure, yeah. Here you are in code, put Ctrl M, L, not working. That just put in here, Ctrl L, not working. If we had left out the assertion at the end of the function, we would have created and returned something that had the right shape as a valid answer but wasn't. Detecting and debugging that would almost certainly have taken more time in the long run than writing the assertion, and this is really useful. But assertions aren't just about catching errors, they also help people understand programs. Each assertion gives the person reading the program a chance to track consistently or otherwise that their understanding matches what the code is actually. Most good programmers follow 2 rules when adding assertion to their code. The first is fail early and fail often. The greater the distance between when and where an error occurs and when it's noticed, the harder the error will be to debug. So good code cuts mistakes as early as possible. The second rule is turn bugs into assertion for or tests. Whenever you fix a bug, write an assertion that catches the mistake should you make it again. If you make a mistake in a piece of code, the odds are good that you have made other mistake nearby, or will make some mistake or a related one the next time you change it. Writing assertions to check that you haven't regressed, in other words, you haven't introduced an old problem, can save a lot of time in the long run and helps to warn people who are reading the code, including yourself in the future, that this bit is tricky. So next is test-driven development. An action checks that something is true at a particular point in the program. The next step is to check the overall behavior of a piece of code. In other words, to make sure that it produces the right output when it's given a particular input. For example, suppose we need to find where 2 or more time series overlap. The range of each time series is represented as a pair of numbers, which are the time the interval started and ended. The output is the largest range that they all include. Most novice programmers would solve this problem like this. Write a function range overlap. Call it interactively on 2 or 3 different inputs. If it produces the wrong answer, fix the function and rerun that test. This clearly works. After all, thousands of scientists are doing it right now. But actually, the better way is write a short function for each test. Write a range overlap function that should pass those tests. If the range overlap produces any wrong answer, fix it and rerun the test function. Writing the test before writing the function, the exercise is called test-driven development (TDD). Its advocates believe it produces better code faster because 1. If people write tests after writing the thing to be tested, they are subject to confirmation bias. In other words, they subconsciously write tests to show that their code is correct rather than to find errors in their code. Second, writing tests helps programmers figure out what the function is actually supposed to do. Here are 3 test functions for range overlap. So we got that, assert range overlap, that is equal to that, assert range overlap, that is equal to that, and that equal to that. Got arrow. The arrow is actually reassuring. We haven't written range overlap yet, so if the test passed, it would be a sign that someone else had and that we were accidentally using their function. So I got the range overlap somewhere. No, not defined, so that's good. And as a bonus of writing these tests, we implicitly define what our input and output look like. We expect a list of pairs as input and produce a single pair as output. Something important is missing, though we don't have any tests for the case where the ranges don't overlap at all. So we got this and we run that. So what should range overlap do in this case? Fail with an error message. Produce a special value like 0, 0 to signal that there's no overlap, or something else. Any actual implementation of the function will do one of these things. Writing the test first helps us to figure out which is the best before we are emotionally invested in whatever we happen to write before we realize there was an issue. And what's about this case? You got this one. Do 2 segments that touch at their endpoints overlap or not? Mathematicians usually say yes, but engineers usually say no. The best answer is whatever is most useful in the rest of our program. But again, any actual implementation of range overlap is going to do something. And whatever it is out to be consistent with what it does when there's no overlap at all. Since we are planning to use the range for this function returns as the x-axis in a time series chart, we decide that 1. Every overlap has to have non-zero width, and we will return the special value none when there's no overlap. None is built in Python. It means nothing here. Other languages often call the equivalent value like null or nil. With that decision made, we can finish writing our last 2 tests, which is like this one. So again, we get an error because we haven't written our function yet, but we are now ready to do so. So we got the function. So take a moment to think about why we calculate the left endpoint of the overlap as the maximum of the input left endpoint and the overlap right endpoint at the maximum of the input right endpoints. We'd now like to rerun our tests, but they're scattered across 3 different cells. To make running seem easier, let's put them in a function like this. So we put every test in one function. So we can now test the range overlap with a single function called test range overlap. We got an arrow which is assertion arrow there. So the first test that was supposed to produce none fails. So we know something is wrong with our function. We don't know whether the other test pass or fail because Python halted the program as soon as it spots the first error. As soon as it spotted the first error, still some information is better than none. And we trace the behavior of the function with that input. We realize that we're initializing max left and min right to 0 and 1 respectively, regardless the input values. This violates another important rules of programming, which is always initialize from data. So next is pre and post conditions. Suppose you are writing a function called average, like define function called average that calculate the average of numbers in a list. So we put in an input in list, number in a list. What preconditions and post conditions would you write for it? Compare your answer to your neighbors, and can you think of a function that passed your test but not his or her or vice versa? So inside the function here we should have some description. The function do what? Take input is a list, and output is what? Output is going to be the average of the number in a list. So that's the function. So when we take input a list, so we can check the length of the list should be at least 1. So from there we can calculate the average of that. So we can design a so the length of the list should be more than 0, or more than or equal to 1. This is it can be called a precondition. Okay. So we can design to get a certain assert, and we can check the length of in list. It should be more than 0, and if it's not happening, we're gonna print out length of the list must be or should be must be more than 0, something like that. And next we get the post condition. What it can be, because we calculate the average, so the average should be at least less than maximum and bigger than minimum. So we had assert, and we got numpy dot average of in list. Maybe average is just a result, average is a function, and that one should be more than and equal to numpy dot mean of in list, and it should be smaller than numpy dot max of in list. And if it's not the case, we get a report called the average should be or must be between mean and max of the list element. So that is a solution. You can enter that one to down there. So that should be a solution, and we check the solution. So we got a post possible precondition, which is the length of the list should be more than 0. So list length must be non-zero. That's a good one. Then the possible post condition can be the average need to be less than max and larger and greater than mean. We're done for that, and we go to testing assertions. We got a challenge, which is given a sequence of number of cars, the function get total car returns the total number of cars. So that gonna get that one, and that gonna get something else. Okay, so it should be returned something like that. Value arrow, invalid letterer for integer with base 10. Explain in words that the assertion in this function check. And for each one, given an example of input that will make assertion fail. So here we got the function, and we run the function again and again. We didn't get total car. Okay, So let's see. Here we got explain in word that the assertion in this function check and check one. Give an example of input that will make that assertion fail. So we have looked at the function in more detail. We got here the first assertion, which is the length of input list should be more than 0. So you can type in the length of input list must be more than 0. The second
can be that each element in values must be, I think it must be an integer. And this one is we got the total, which calculate before that. So total must be more than 0. Just that, and we run that. Got the function, and we get the total. That we run the function, and it's working. But if we get that one, it's not working. It would throw out that the invalid literal for input base 10a. So it should throwing out the integer assertion for us, but it didn't throw that. Very sad. So let's see the solution. So here we got that the first assertion checks that the input sequence values is not empty. Yep, so it makes sense. The second assertion checks that each value in the list can be turned into an integer. Okay, it must be an integer, maybe. And the third assertion is that the sum should be more than 0, and this kind of thing should be fail. Okay, so we're done for that, and we come back to the beginning. We review the key points again. Got program defensively. In other words, assume that errors are going to arise and write code to detect them when they do. Put assertions in programs to track their states as they run and to help readers understand how those programs are supposed to work. Use preconditions to check that the inputs to a function are safe to use. Use post conditions to check that the output from a function is safe to use. Write tests before writing code in order to help determine exactly what that code is supposed to do. And that's it for section 10, defensive programming. I'm closing that and closing that on the left there. And the next section is going to be section 11, which is debugging.